So here I start. Okay, good morning, everybody. I'm Kirtan Adhikari, faculty at College of Science and Technology, and here is my brief slides. Okay, let me take you through my presentation, and if you have any doubts, I'll be very glad to clarify your doubts at the end of the presentation, or in between. If you find anything and my voice is breaking, or if you want to stop it me in between, please feel free. Okay. So today's lecture is all about the river network modeling using HES-RAS. Why I call it river network modeling is because at times people tend to confuse with the flood modeling and other stuff. Here, river network modeling is the HES-RAS has the capabilities to model various dendritic system of rivers. So if you have the data available with you, you can model 1D or you can go for 2Ds. Now, I will start off with 1D modeling and then gradually move to 2D. Okay, so let's start with this. First thing, the Earth is very complex, the Earth is very, very complex to comprehend all the physical processes that occurs. And it may not be, it could never be fully understood. But in the absence of a perfect knowledge, when we don't have the perfect knowledge, we still can predict the behavior of such systems. Now, what I call by predicting behavior of such systems is we have some established mathematics that governs the physical laws that governs how object moves. The best example I can throw here is just throwing a projectile. You have a projectile in your hand, you throw at some angle with some initial velocity. The trajectory of that projectile is estimated using Newton's law, and that is exactly what we are doing in river modeling. We have some equations, that is what we call by shallow water equation. It was developed by Saint Venant in earlier 17th century, and that governs the fluid behavior, the behavior of the fluid and its interaction with hydraulic structure. So that is what flood modeling as a holistic description, if I have to give, you're basically trying to solve the shallow water equation and then trying to estimate how the system will behave under different stimulus. Here, stimulus indicates the boundary conditions or different flood hydrograph that you are impinging in your study area. Okay, and finally, the main reason of doing a flood modeling is you can then have this flood hazard map. And why do we need this flood hazard map is, with the help of this flood hazard map, it helps to strategize our planning for development. The main reason is to develop the strategic development, okay? If we don't have this hazard map already with us, then there is lots of confusion as of how much the development activities has to be carried out in a particular region. So with the help of a hazard map, we can pretty much estimate how that area would look like when there is a flooding situation. So having that information, it helps us it guides us. In fact, it guides the policymakers and the development activity around the region. That is the basic understanding of why people use modeling. Now, HES-RAS is one of the modeling, and it is widely used for one reason, that is it is free and it is well tested by experts. There are other counterparts like Mike 11, Mike She. There are so many other commercially available softwares, but HES-RAS can pretty much do all the nitty-gritty stuff that is usually done to develop the HES-RAS, the flood modeling and flood hazard maps and other important characteristics of hydraulic structures during different flooding environment, during various flooding situations. Okay, so that is the basic introduction to the why we do flood modeling. And by the way, let me also be very clear. My presentations are intended for the beginners who are just starting with modeling. Those people who already have an experience with HES-RAS modeling, they will find this very rudimentary and very basic. But I believe it is for those who are just starting, and I believe you'll have a lot to take from this presentation. Okay, now let's understand this flood modeling much more in detail. Okay, So number one, you need to identify your study area. From the look, you can see that our world is very complex. From this small portion of Earth, I would like to say that our world is very, very complex. And to do modeling, you using this complex environment or complex geometry or complex the nature of topography, it becomes, it is slightly impossible for us to take into consideration all the factors. So what we do is we simplify things. We simplify things by, now this is three-dimensional world. This is three-dimensional world. Now to simplify this, we just take it as two-dimensional data. Now this is a two-dimensional data. We do cross-section. We measure cross-section exactly 90 degrees to the river, and then we take out something like this, cross sections. You can see this is a cross section. Now three-dimensional Earth is now you have already made into two-dimensional. You have simplified things. Now to do the flood modeling, you also need the data. So that data, now next comes the data preparation. Now there are three types of data basically when you use HES-RAS. Okay, and now I'm talking explicitly in terms of HES-RAS modeling, not any other modeling, but just specifically to HES-RAS modeling. So there are three types of data: geometry data, the flow data, and the boundary data, boundary conditions. Now, geometry data, as I already have mentioned, you go to the field, you do surveying, you take out the cross-sectional information. That is your geometry data. On top of that, if there are some hydraulic structures like bridges, like weirs, like dam, if you want to put information, that information also you have to acquire through surveying, or yes, of course, surveying, or if somebody has already proposed a dam and the dimensions is available, you can simply adopt that dimensions. Okay, so that is the geometry data. Next comes the flow data. Now there are two types of flow data. One is steady flow and another one is unsteady flow. Here, steady flow and unsteady flow. Now, why I'm emphasizing this is because HES-RAS has a different scheme of solving steady flow, and HES-RAS uses a different scheme to solve unsteady flow. So that's why it's very important that what we are intended to solve for. Is it the water surface profile? If we are interested in water surface profile, then we consider only steady flow. In steady flow, just put one discharge value, just peak discharge or any discharge that you are interested. You impinge that discharge as a boundary condition. Another unsteady, the discharge is a function of time, which is in a form of a hydrograph. Okay, so an unsteady case, as a definition, unsteady means discharge that varies with time, right? So the boundary condition here is for unsteady case, you should have the hydrograph with you. For steady case, even one discharge value if you have, that is fine, because for steady case, HES-RAS uses energy principle to solve, while for unsteady case, HES-RAS uses Saint-Venant equation. Okay, so having this data in front of you, so this is the requirement. First thing is the requirement. This data, you should have it before you proceed. Next thing is you also should have a very powerful computer. I will tell you why later on. Now, this equation is solved. Now, this you can see the processing is happening in the computer, and the computer basically simplifies this. Computer basically solves the equation that is already established mathematics. Okay, that is in fact you are solving an equation using this data that you have provided. You are solving it. Finally, you will get something like this, a hazard map. And for engineers and for planners, this is what we are looking for. So the flow line, the approach in modeling is you should have the data, you should have a very powerful computer, and then the computer does the processing. When you put the different inputs, computer does the processing, and output is in the form of visuals like the map that you can see on the right. So this is what is exactly happening when you do HES-RAS modeling. So again, once again, for three-dimensional Earth, it is very complex to solve problem. The three-dimensional Earth is made into two-dimensional by taking cross-section surveys. Okay. Now, when I say two-dimensional, this is not two-dimensional processing. I'm saying the three-dimensional Earth is converted into two-dimensional by just taking the cross sections. You're simplifying things. That is what I meant. Now, two-dimensional processing, I'll come to this point later on. The processing concept of one-dimensional and two-dimensional is slightly different. Here, by meaning of three-dimensional and two-dimensional, I mean that three-dimensional Earth is simplified into two-dimensional just by taking only the cross-section at a regular interval. So that is what I mean. After that, you should have a data, the flow data. The flow data can be steady data or unsteady data. If you're interested just for the surface profile, one data, one QP or the discharge data is more than sufficient. If not, you should have a discharge data that varies with time, which we normally called it as hydrograph. Okay, so now comes the question why we need to do the modeling. So in the first stage, as I have already in fact explained, in this image, you can see that it has already flooded. Now, our understanding is if this, before the city was, before this development happened, if this river was modeled and if the system, if the behavior of the system was identified, this would have never happened. That is the concept, that's what I am saying. This could have been avoided with proper planning. So proper planning in the sense, before any development activity is going on for any area, any region, we can simply take this river, take out this river, make some cross sections of it, make some cross section and do a simple flood modeling. So we know that when the discharge of peak of something Qmax, let's say X meter cube per second is passing through, how would this area look? Now, of course, it may not be 100% accurate, but it will give us an understanding that what would be the flood level, what would this area, how would it behave when this flood is coming? So basically, keeping that as a basis, we could have constructed levees or any other structures that could have protected this land. So that is why we do modeling. When we talk about flood modeling, we don't emphasize much more into we do not emphasize more on accuracy, but in fact, it should be a guiding principle. Of course, academicians always argue on accuracy, but in real practice, because our data itself is not very accurate, like three-dimensional is converted into two-dimensional, so there are so many approximations. Instead of going to very accurate results, we have to take that as a basis for planning. So that is what distinguishes from the flood modeling with any other type of modeling. Of course, a great deal of caution has to be exercised while you do the modeling, because the completely wrong model would then give you a wrong result, which will be not very useful for planning. So having that much of understanding of HES-RAS, let's go into the actual HES-RAS software. Okay, when you first open this HES-RAS, you will see something, a window something like this. Okay, and here HEC means the Hydrologic Engineering Center. It is based in California, and RAS is the River Analysis System. So when you, for the first time, if you open, it's a very, very useful, user-friendly tool. Okay, so when you open it, it just a small window pops up, and there are few options like edit, run, and view. These are the most important options. I mean, for most cases, you will be only using these three options. Now, if you need to put geometry data, you just click on the geometry editor, and then you start putting your geometry data. So first you create a project, and this plan means for one particular geometry, you can run number of situations, right? For same case, for this case, let's take this case. Once you have the geometry and you want to supply the boundary condition X as X meter cube per second, you run with X meter cube per second. You're not satisfied. Again, you want to run with X plus 1 meter cube per second. So you can simulate a number of times. For that reason, there is a plan. So plan means what situation you are running it. So if you're running for different setup, then you can name a plan. If you are running for different setup, then you can, again, with the same geometry, with the same boundary condition, but by changing the inflow characteristics, you can run number of times. So once you have set up your HES-RAS model, once your geometry is fixed, once your all the other stuffs are fixed, then you can run same model number of time for different situations. So that is what plan means. Geometry is, like I said, the geometry of the entire cross section or the entire reach. And there are two options. Either you can run for steady flow or you can run for unsteady flow. So it's very straightforward. There's, it is not very cumbersome. It is very straightforward, and anybody who is starting with the HES-RAS can get along with the HES-RAS in a very short period of time. So let's talk about the input data now. Like I said, input data, the most important data is the geometric data. Okay, geometric data means all the river system, the cross sections, and one convention that the HES-RAS uses is, if the river is flowing in this direction, you stand here and look towards the flowing direction. Your right hand side is going to be right of bank and your left hand side is going to be left of bank. Okay, so let's say this is the river center line. So this is your right of bank and this is your left of bank. So this is the sign convention for HES-RAS. So while you put the data, you have to make sure that the Mannings coefficient for left hand side and for right hand side, you put it differently. Okay, I mean, there's a flexibility to give different Mannings for different reach length. Now if I just make a cross section here, let's say this is a cross section and this is your floodplain. So here the Mannings would be different than the Mannings here. So HES-RAS also gives a facility to give different Mannings values at different region. Okay, so that is what I mean by river system. And if there is another river coming here, you can simply just join this river here, make a junction, again provide this cross section. That's it. Okay, but you need to have the data set with you. And one more important thing is the reach length. Reach length is the length between two cross sections. So this is the reach length. Now, interesting thing is, this reach length is, if your river is meandering, then reach length won't be equal. Okay, so here, if your river is going, let me use a different pen here. If your river is something like this and your cross sections are like this, it has to be perpendicular to the flow. Okay, it has to be perpendicular to the flow. So you see the reach length here, for same reach, the reach length is at this side is small. So for this reason, the reach length has to be different. Okay, I mean, the HES-RAS gives you a flexibility to provide different reach length, because when the reach length, when the river is curving, then the reach length is different. Okay, so HES-RAS gives you a facility to provide the different reach length at different location. For the same reach, the reach length at the left of bank and the right of bank, the left of bank and the right of bank would be different. So that's why HES-RAS also gives you a facility to provide different reach length at the same reach. Next is the hydraulic structures. So hydraulic structures like levee, dam, barrage, weirs. HES-RAS also provides you an option to provide this information. And the most important parameter is the Mannings Roughness coefficient. This is kind of a very important Mannings N. This is very important parameter, but at times we try to be very ignorant about this parameter. It's one of the most important, in fact. See, one thing is we rely completely on standards that is available to us through some kind of a standard textbook, right? But many researchers have claimed that the Mannings behaves kind of differently. Now, just as an example, that recently I was working on this. Okay, if your cross section is like this, and for, let's say, the water depth is here, the Manning here would be something different. Let's say Manning 1. As the water level increases, the Manning, equivalent Manning, that's what we call it. Here at this level, the Manning would be something else. In the same river cross section, Manning varies. Manning is a, it varies in X, in Y, and it's Z, and also it varies in T, in time, because you must have observed that during summer there is lots of vegetation. During winter, that vegetation won't be there, right? So this Manning is something very important. So I highly recommend not simply plugging in the value through some standards, but to do your self research, and not research in the sense you just go to the field and try to verify the Mannings. Very important, at times ignored in most of the cases, but it's very, very important. The Mannings that is given in standard may not apply. But one limitation of HES-RAS is Manning can vary along X and along Y. Okay, in HES-RAS, the Manning you can vary along X and Y, but you cannot vary along Z and T. Okay, so this is one limitation in HES-RAS when you do the simulation. When I say Manning varies in Z, what I mean is the Manning that varies with respect to the depth of water. So that maybe in future they are going to incorporate or not, that I don't know, but this is one limitation. Another one is contraction and expansion coefficient. By default, HES-RAS has provided some expansion and contraction coefficient, but you can still work on and try to give whatever fits the best for your case. Okay. And finally is the flow data. Flow data, like I explained, it is unsteady and steady, right? You can either put one discharge value or you can put a complete hydrograph. If you put one discharge value, the scheme that HES-RAS uses to solve the problem is different. It uses energy equation. If you put unsteady discharge, like if you put a hydrograph as an input, as a boundary condition, then it is going to use the Saint-Venant equation to solve the problem. So you have to, as a researcher, you may have to decide what you are interested in. Either you are interested in the surface profile, or you are interested more into the interaction of flood with the hydraulic structures. Okay, so let's go one by one. When I talk about the geometric data, which I have already explained here, take a small, dendritic system of the, catchment, wherever you are interested to model. So for instance, if you're interested to model between A and B, of course, you can model entire reach, but only thing is you need a very strong computer to process all this. Moreover, you need data set. Okay, so this data set limitation could impose, this can impose a limitation for you to do the entire catchment study. So for that reason, we just take a small study area of length L, let's say, so A and B here. Now, same thing is, done in HES-RAS in this fashion. Now, you may think this is coming time and again, okay, whenever I do give this lecture to my students, the one thing that the students always will ask is, sir, your river is meandering, but when you draw it in HES-RAS, why you are drawing it straight? So that is always there. My students will always ask this question. So I know some of you who are doing for the first time may be having the same doubt. So the reason is it does not matter to HES-RAS, because we are using one-dimensional flow, one-dimensional equation to solve our problem. One-dimensional equation is we consider velocity as the component of velocity is only in the forward direction. So it does not matter here. The only difference is the velocity component has in X, and now if we take this as an XY plane, this Y and this XY plane, here the velocity will have this component, right? It will have something, this component. But because we are using one-dimensional, HES-RAS will ignore this and only take the component, this component, the flow direction component, okay, where the flow is taking place, not the other direction, okay, along the flow. So HES-RAS will ignore all the components and only take into this velocity component. That's why it does not really matter whether you draw this in a in a zigzag fashion or you make a straight line. It's all the same. only difference that you can provide is through the help of a reach length. If your river is meandering, and you know at which section it is meandering, of course, from your data, you will have this L and L dash different values, because whenever there is a meandering, of course, one side will be less, another side will be more. That is the only information you can put in HES-RAS. Or else, if when you construct the geometry, by the way, you have to construct this yourself, okay? So in one-dimensional flow. So when you construct it, you can simply click one point, click another point, it will simply make a river. So that is a hypothetical river. With now you need to provide the cross-section information, okay? Yes, now it comes the cross-section information. Like I said, for cross-section information, you have to go to the field. There's no other way. You have to go to the field and do surveying. So this was when I was a student at here in the university. We did a flood modeling as a project. So at that time we went to the field. It was an exciting project. So this was the bathymetric survey. We also call this as a bathymetric survey. This portion is known as the bathymetry, and the surveying is known as the bathymetric surveying. Okay. So now this is what I was explaining in the earlier slide. As you can see, there's a different type of forest in this region, and there's a different type of forest in this region. So obviously the manning would be different from this region, right? So manning is going to be different. So let me put this as N, N2, N3, or N4, right? So manning would be different. As I said, manning can change in forward direction or in lateral direction, not in the depth direction. So this emphasizes that for all the depth, the manning is same as what you have given here. So that is there in HES-RAS. So you can simply put the Manning's value here. You can see for this case, there are different Manning's value. So for this region, as you can see, it is 0.14. And in between this, it is it is here 0.14 again. And here it is 0.1. So you can see that HES-RAS has the abilities to provide different Manning's coefficient, okay? So once we have the cross-section information with you, next is you also need the Manning's roughness. Of course, the most important Manning's roughness would be the Manning's at the channel. So for this, you can do the velocity measurement and then confirm the Manning by yourself. Instead of directly choosing it from the standard, you can simply do a flood velocity measurement, and from there you can take out the Manning. We know that velocity is 1 by n r raised to 2 by 3 root of s naught. Considering this is a steady flow, when you go to the river, of course don't go during the flood situation, just go during a normal situation and consider this as a uniform flow. And from here you would have measured the velocity, and then the only unknown parameter becomes n, because r you are calculating through the topographic survey. S naught you would definitely have as you have the survey data. So from here you can estimate n, and then supply that n would be preferred than choosing any n from the standard table. Okay, once you have the geometric data, next is, of course, this also comes in the geometric data, the hydraulic structures. Okay, now I'm putting everything here. The weirs and the bridges and everything together as a hydraulic structure. So for hydraulic structure, most important thing that you need to have, the data that you need to have, is the elevation of this point, just the elevation of the top level. If you have the elevation of this top level, then you can construct this. You are constructing this yourself in HES-RAS. So if you have this information of the deck elevation and the location of these piers, then of course you can construct this. Only data that you need is the elevation of this deck level. Okay, rest you can construct it in the HES-RAS. Of course, if you have this width and the location of a piers, then it's going to be added. It is going to be useful. But if you don't have it, you can simply approximate it. Okay, so most important data, if you are wondering, is only the elevation of this deck level. Once you have the elevation, you can construct the entire bridge. Another concept that HES-RAS also gives us is the ineffective flow areas. So ineffective flow areas means this area is not conveying discharge, meaning flow is not taking place from this region. Although there is a water here, there's a pond of water here, if I just make a three-dimensional here, water is not flowing from this ineffective flow area. Okay, so you can in your model you can give this regions where you feel that water will not be, usually this under the bridge, if you extend this bridge, the upstream of this bridge, there will be water, but it will not be conveying the water, right? So that is what ineffective area means. So I have already discussed about the Mannings roughness coefficient, right? And let me not go in depth into this Mannings coefficient here, because as I said, it would be wise to go to the field and take the values yourself rather than simply relying on some standard values. And there's another concept of contraction and expansion coefficients. By default, HES-RAS is given, but if you want to change that, you can also change it. And finally, the flow data. Most important thing is the flow data. As I already have explained, you can provide one discharge value, just one P, one Q, or you can provide a discharge with respect to time in the form of a hydrograph. You can also provide a stage hydrograph. Okay, stage hydrograph means normally in a river, if you are coming from pure academic, then you may not have an experience. If you come from the field, you will definitely understand that at the riverside, people don't measure discharge. Okay, they only estimate discharge. What they measure is the depth of flow, and what they do is, once you have the depth of flow, they establish something known as a rating curve. From the rating curve, they estimate discharge. So this discharge is in fact coming from the rating curve. Okay, this data is, the discharge is in fact coming from the rating curve. Now at times what happens is, if you don't have the rating curve, but if you only have the stage hydrograph, that also you can provide as the boundary condition. So it is not necessary that you have to provide the discharge. You can also provide the stage hydrograph as the boundary condition. That is also fine. HES-RAS has the ability to take in either discharge hydrograph, or it can take in the stage hydrograph. Okay, finally comes our boundary conditions. So like I said, there is two boundary conditions. Boundary condition at A, boundary condition at B. If you forget about the tributary, then there is only two boundary conditions: the upstream boundary condition, right, upstream, and the downstream boundary condition. But if there is a tributary, that the inflow hydrograph also has to be provided from the inflow, right? So that boundary condition will also add. Now, if there were another river tributary coming here, then the boundary condition, you also need to provide a discharge at this point. So that also acts as a boundary condition. So for this cases, okay, for this example here, I have the upstream boundary condition point at A, I have a downstream boundary condition at B, and I also should have this image is cropped from the bottom. Okay, so there should be one more boundary condition at C. Okay, so this image is cropped, so there has to be one more boundary condition at C, or else the program is not going to run. So as you can see, for A, I'm putting the flow hydrograph as the boundary condition. So this is the upstream. Okay, from at A, I'm putting the flow hydrograph as the boundary condition. You have an option to put stage hydrograph, flow or stage hydrograph, the rating curve it has, and there are so many other things. Now, this is not for the channel, but it is for some hydraulic structures. Okay, other boundary conditions are for other hydraulic structures. And another important thing that we sometimes tend to ignore is the boundary condition at the downstream side. Normally, what we do is HES-RAS asks us to provide the downstream frictional slope. It asks us to put a frictional slope, but obviously nobody will have a frictional slope at the downstream boundary condition. But since frictional slope is the rate at which energy is lost, right? So no, I mean, most cases this frictional slope is not available. So we tend to approximate this as the bed slope. So at this case, So you can understand this is also an approximation. So like this, I have been explaining, right? So you have to make so many approximations while you do the modeling. So the result that you get is not 100% accurate, but it will act as a basis for planning. So that is what is important to understand here. So for downstream boundary condition, you can provide either the critical depth. Normally, HES-RAS will ask you SF, but what we do is we put the S0 as the boundary condition. But you also have a flexibility to put the critical depth. The critical depth is the depth at which there is a minimum specific energy, right? So that also we can put, but the thing is, what we are telling to computer when we say critical depth is at this region, the flow is critical. At this region, at B, the flow is critical, which may not be true, okay? So the best way to deal with this situation is simply put S0 with the understanding that slight errors can be expected at the downstream cases, okay? But if you have hydraulic structure downstream where you are definite that the flow at B is critical, then you can put critical depth as the boundary condition. Then it will be fine. Okay, now comes the processing part, okay? Although HES-RAS has steady flow analysis, okay, it is one-dimensional. The unsteady flow analysis, it is the one-dimensional, okay, and also it has two-dimensional. Now it supports two-dimensional. In my case, in today's lecture, I will be discussing steady flow analysis and one-dimensional unsteady flow. Although I have included two-dimensional flow as an example, okay, but hydraulics of two-dimensional is off the scope of this slide. So I will not be discussing the hydraulics of 2D modeling, but I will show you the results from 2D simulation. HES-RAS also supports the sediment transport. As a matter of fact, I have never used the sediment transport myself, so I will not be an expert to deliver a lecture on this, but it has the capacity to do the sediment transport. Recently, they have also included the debris flows, okay? Recently, they have also included the debris flows and non-Newtonian flows. I have not experimented. Very new feature in HES-RAS 6.1. In HES-RAS 6.01 or HES-RAS maybe 6.1. In this version, they have included debris flows, okay, which is non-Newtonian flows. HES-RAS also has the capability to do water quality analysis, the BODs and other stuff, that how it disperses in the flow. It also has the capability of the bridge scouring, and finally the inline structures like barrages and other stuff, and also the dam break analysis. So you can do this much of analysis. More than this, I have not included the debris flows. This is very recent, okay? This is very recent. They have just added in the latest version the debris flows and the non-Newtonian flow. I'm yet to experiment on it. So today's lecture, I will just be discussing about the 1D steady flow analysis and 1D unsteady flow analysis. Sorry for that. Okay. All right. Now, after having everything set, final stuff is now you choose which modeling you want to take. Now, you may be interested for 1D, 2D, or steady and unsteady. What is your interest? What you want to process? So if your interest is to process for steady flow analysis, then you simply choose this steady flow analysis and run the program. After running the program, now HES-RAS has this the options to visualize your results. First thing is you can visualize the cross-section plots. You can visualize the profile plots, general profile, rating curves, the perspective. This is three-dimensional view. Not very nice. You will not be very pleased with looking at this perspective view, but in two-dimensional, it is much more pleasing. And finally, the tabular result. If you are an engineer, then you will be mostly dealing with this result, okay? Other things are just to show, just to present, but this is more important for hydraulic engineers. So let's see what it is. the first one is the cross-section plot. So you can see this is the steady flow case. Okay, for a steady flow case, so you can see at a particular river cross-section, at that particular discharge, the water level is at this height. Okay, so that is, so it's a simple thing. It's just for presentation only. There is no more information available here. So it will, HES-RAS gives you this information. Next one is the profile plot. This is useful. Okay, you can see the backwater curves and other important aspects. If you're doing a channel design and you're not sure of, because of the construction of bridges, you have to constrict your channel and you want to do the analysis as what would be the backwater curve. So that time it becomes very, very useful to see how the backwater curve behaves. So profile plot is, your river is here like this. Okay, river is here, this cross section. Okay, this let me put it as profile, so PP. So this cross section you are visualizing with the in HES-RAS. So you can see here there's some kind of dam is here, and from here you can see the water profile. So HES-RAS has all these capabilities. But as such, for my experience, this is only for visualization purpose. Mostly, if you're interested to do any further analysis, then of course you have to go into the tabular values, because that will give you more important informations like frictional slope, the number of iterations, and the error. That is also important. Sometimes what HES-RAS does is it's an iterative process. Okay, it uses iteration to solve the energy equation. And when it reaches about 20-30 iterations, I forgot the exact number, I feel it is 20. When it strikes the 20th iteration and yet it could not converge towards the answer, then it will simply take that as a value, and HES-RAS will give that as a warning or an error. Okay, sometimes that happens. So finally, if you don't have HES-RAS, the rating curve at a particular cross section, HES-RAS also gives a rating curve. Okay. Now, why I'm showing this is important. From the rating curve, you can analyze whether your model was stable or not. Sometimes what happens is your HES-RAS will run. It will simply run. It will give you a result. You will be very happy. But when we analyze this rating curve, you will feel that it has gone something like this. So from here only you can make a sense that although the HES-RAS did not indicate any issues, but you need to understand that there was some kind of instability in the program. You may have to change some parameters in your geometry or your flow data, and then again simulate the cases again. Okay, I have observed this number of times. HES-RAS is running absolutely fine, but when I check the rating curve, it gives something like this. So from here you can make a sense that it was not correct. Maybe it is because it has reached 20th iteration, it could not converge, and then it took the same value. Because of that, the error was persistent in the rating curve. So this is one way to analyze whether your program actually is working fine or not. If in unsteady case, if there is some issues, then the solution will blow off. What I mean by solution blowing off means, it's a slang, modeling concept that your program is becoming unstable. Okay, so rating curve is one case where you can visually see whether the program has run fine or not. My first thing after doing simulation is to go and directly check on the rating curve. If rating curve is coming fine, then of course I can rely on the data. If the HES-RAS is not giving any issues, yet the rating curve is fluctuating like this, then I need to once again check my input data set. So very important. Okay, this is one important thing that with experience I have got to know this. And finally, not very pleasing, right? Three-dimensional plot. I mean, I don't think anybody would be really impressed to see this, but yes, the HES-RAS gives us this perspective plots. So there's nothing very fancy about it, just three-dimensional plot. And now it is, I think in the future versions, they are going to completely do away with this perspective plot, because it's taken over by the two-dimensional. In two-dimensional, the graphics is much more, appealing to eyes to see. Here, this three-dimensional plot is not actually, I mean, just for presentation, it's fine. And the last and the final one is the tabular plot. This is where most of the engineers would be investing your time. So after running, so this is for steady case, okay? This is just for a steady case. Is taken out from the Godavari Sabri reach. So we were also doing some steady analysis there. Just one-dimensional analysis we did. So that time I took out this tabular form, the results. And HES-RAS also gives us the flexibility to solve in, the mode. We can choose the mix mode. Mix mode means it is critical. We know, right? It is critical, subcritical, or I mean, there are two types, right? So mix mode means when you're doing a simulation, it also handles in a sense, the Froude number fluctuates below 1 and above 1. That is what it means. So there's a chances of Froude number going very high and very low in your same case. So for that, if you anticipate such cases, then you can run for mixed mode. So to summarize everything here, the HES-RAS has 3 steps: input, processing, and output. So input is there are 3 again. In input, there are 3 cases, right? First, you put the geometry data, and then you put the boundary condition and the flow data. So these are and also the Mannings roughness, the roughness. So roughness, there are 3 input parameters. Then you choose processing. Now we have steady, 1D steady, 1D unsteady, and 2D unsteady cases. So you choose what you want to solve for. And finally, output, you can visualize, like I have shown you, the cross sections you can visualize, the profile you can visualize, the rating curve you can visualize, and also the errors you can visualize. For engineers, I believe the errors and the tabular data is much more important for us than this 3D cross sections and other 3D cross sections. Mean the profile, the perspective plots, that is only for presentation purpose. It is not very useful. But for engineers, the tabular data and errors definitely is very useful. Okay, and also the rating curve. And rating curve is, I mean, this is not a standard process, but I usually check the rating curve. It is stable. I understand the program went well. If it is not, then we need to understand that there was some problem in your simulation. Okay, so finally, to summarize everything, what did we just accomplish? So we say we did modeling, and what exactly is modeling? So to summarize everything, our physical world that we live in is very complex. We can simplify it by ignoring factors that are insignificant in the study. For instance, although we are putting river, discharge, and there are so many other aspects, because the density of water is not 1,000, right? When flood water, the density of flood water is not 1,000. Yet we put 1,000. So these are some of the assumptions we make. Moreover, there will be evaporation, there will be infiltration. We did not take into consideration, because this is insignificant when compared to the peak discharge. The value is very insignificant. So we simply simplify things by not considering other factors. By simplifying the system, it enables us to predict the behavior with the help of established mathematics. And in open channel, the mathematics is the Saint-Venant equation. And there are 2 equations. One is the continuity equation and one is the momentum equation. Here, I have given you both are the momentum equation. One is in conservative form, another one is non-conservative form. Non-conservative form means the variable here is in terms of depth and velocity. You are trying to solve what would be the velocity at different time at different space. So if you try to solve velocity, we call it as non-conservative. If you're trying to solve for discharge, the variable here is discharge. If you're trying to solve for discharge, then we call it conservative, because it conserves the mass, right? Moreover, the conservative form is stable for a case rapidly varied cases, because in the rapidly varying cases, the mass flux. The discharge means simply mass flow rate. So mass is conserved, whereas the equation may blow off during rapidly flow, especially in the case of dam breach and hydraulic jumps. The non-conservative equation may blow off because the velocity then breaks, right? So that's why HES-RAS uses the conservative form to simulate for these cases. And finally, the models simulate different scenarios and help predict system behavior under different stimulus. So like I said, you can, once your geometry is fixed, you can impinge with different discharge data to understand how the system would behave under different situations. So that is what exactly is the main, the concept that revolves around modeling. So before I move ahead, I will just like to have 2-3 minutes break so that I can drink some water. So in case if you have any doubt, I'm there. You can just throw your questions. So, okay. So can I continue now?
Yes,
Yes, sir.
please continue.
Okay. Thank you for the response. Okay, now let's get into how this computer actually solves this equation. So what is happening behind the scene is, for most cases, a numerical method is used. Okay, numerical method is sometimes known as numerical techniques. So what we do is we divide our system into two-dimensional grids, like I have shown here. I'm not going to mess up here. So I have already shown here, and what we do is the next time step. So this is the x direction. Okay, so this x direction is the forward towards the flow, and here it is the in y, it is the time direction. Okay, so time direction, in a sense, I'm just taking as a very loose term as a time direction. I'm just simply saying that it is in time dimension. Okay, so what we do is we use some kind of numerical technique. In numerical technique, there are two basic schemes. One is explicit scheme, another one is implicit scheme. So in explicit scheme, what happens is the unknown at the next time step. So let's say this is the unknown, okay, where we are interested to calculate discharge or velocity. If you are taking the non-conservative form, you will be interested to calculate velocity. If you are taking into the conservative form, you will be interested to calculate the discharge. So at this time step, at the forward x grade, at the next time step, if that is the interest, that is our interest. In fact, that is what we want to calculate. So to calculate this, if you use the known values at the previous time step and the previous cross section, I can say that previous cross section and the previous time step, if you use this value, then the system becomes explicit, meaning we simply can approximate means calculate the value at the next time step at the forward cross section using the previous information, and the system will become and explicit. We calculate for the first time, we calculate the discharge at this point. Next, we calculate using this three information. This is also known as the initial value, okay? So using this three information, we calculate for this one, and we go marching forward, okay? So this is the explicit. We don't need downstream boundary condition because we simply go on calculating the next discharge. Similarly, for next time step, we again use the previous time step and we go calculating the values. However, in implicit scheme, what happens is we use the information such that in every time step, instead of a value, we get an equation. So for particular time step, in this case, j plus 1 time step, instead of having one value, we'll have system of linear equations. Okay, so that system of linear equation is converted into a matrix form, and that matrix is solved. So that is what we call by implicit method. Now, difference between explicit and implicit is explicit is not very stable. Implicit is highly stable. So HES-RAS uses an implicit method to solve the equation. Okay, so the advantage of explicit method is you don't have to solve the matrix, and at times solving a matrix itself becomes a huge challenge. Okay, so that is the advantage of explicit. But the condition, the stability condition for explicit is you have to take a very small delta t and very small delta x, whereas in implicit method you can take fair amount of delta t and delta x, so it can have it is stable for a quite range of delta t and delta x. Okay, so this is the most simplest form of routing a river in the channel. So that is the kinematic wave, whereby the momentum equation, which is SF is equal to S naught minus del Y by del X minus V by G del V over del X minus 1 by G del V over del T. So this is the momentum equation in non-conservative form. As you can see, I have just put the velocity terms, right? So in kinematic wave, what we say is all this is neglected. So SF is equal to S naught. So if we consider SF is equal to S naught, then our equation simplifies to an extent that you can do the calculation at the discharge at this point using this equation. So I have used this is a kinematic wave, but of course there is implications. You cannot simply use kinematic wave wherever you like, because kinematic wave has its own property. For a flat terrain like in India, kinematic wave is at all not suitable for your case. Kinematic wave is fairly suitable in my case because it's a mountainous terrain. The wave behaves much more in a kinematic fashion than in dynamic fashion. So for Indian case, kinematic is absolutely not it's not to be used. Okay, that's some extra knowledge, nothing to do with HES-RAS anyways. Okay, just an extra knowledge. All right, so finally we say we solve this equations, right? But how exactly this equation is solved? So just as in case for those of us who have just forgotten the basics of calculus, just for them, moreover my slides are for students, so that's why you can skip. Those of us who are already aware of it, you can simply ignore this. Okay, so what we do is we find the derivative terms from the basic definition of derivative, that is the slope, right? So just a case, just for an example, let's take a function value of x squared, and we want to estimate the slope using keeping the x grid as the distance of the small change as the delta x as 0.2. So from this equation we get to know that the f dash, the derivative of this function at the value of 3 is we're getting 6.2. Analytically, if we solve it, we know that the derivative of x is 2x. By this, we get the function value 6. So we know now there is some issues here, right? In numerical technique, this issue is what we call by truncation error, right? So if we actual value minus this value, if you do, so there is some value is it is overestimating. Yes, the problem is this is additive in nature. Additive in nature means for one time step there is some error. For next time step, it will go on adding this error, and finally you will get a very wrong solution. Although your model is running fine, absolutely fine, no problem, but yet the answer that you are getting is wrong because of this inconsistency in the technique that we are adopting. So that is what we really have to understand. Although the example is very, very simple, but it gives a very good information regarding, although your system, when you run it, like in my previous example, I said system is running, everything is fine, but then yet you get a zigzag, the rating curve. This could be a reason, I cannot tell for sure, but yes, of course, when we are doing so many approximations, such errors are persistent in the model. And this is not just true for HES-RAS, it is true for any numerical technique. To reduce this, people have used different forms of schemes to solve the numerical the equation, okay, the equation numerically. So finally, here comes the most important thing: how reliable are these models? I see some errors in previous examples, so here there's some errors, right? So that is what I was referring to. And likewise, the purpose of modeling is to understand the system behavior under various possible stimulus that would be help for decision making. That is the main fundamental idea behind all this modeling. We don't want to exactly find the solution, but it should give us something based on which we can plan, we can make decision. If the modeler, like you and me, exercise cautions while preparing input data, initial condition, and the model can provide realistic results. Okay, so what I mean to say is, if our numerical technique is very stable, if the input data is correct, if the Mannings roughness that you have used is absolutely fine, if it's correct, then yes, the result that a model generates is realistic, we can believe in it. However, the model must understand the limitation of the model and mathematics. Like in my previous case, I'm using kinematic. Although if you run kinematic, it will simply run and give you some values, but kinematic for India is not suitable choice. There is a limitation there. So these limitations one has to understand. And finally, I would like to emphasize with red and bold, okay, that is garbage in, garbage out. That is true for software, any modeling. If you put some garbage values to a software, the software will give you garbage back. So this is something that we all must understand about the modeling. We don't say it is 100% accurate, but at the same time, it should not be 100% wrong, right? So this is what we need to understand of modeling. Now, handling errors. So we know that there is some issues. We have made so many approximations. So how we can deal with these issues, in particularly in HES-RAS, the error gets introduced when we have inadequate boundary conditions and input data set. So like I said, the downstream boundary condition, because HES-RAS uses the implicit method, it requires a downstream boundary condition. So by default, HES-RAS will ask you the frictional slope, which of course nobody will have it at the downstream boundary condition. So that time we put the S naught, the bed slope, as the boundary condition. Now, what would be the difference between SF minus S naught? Whatever the value comes, that will act as an error. In a simple sense, that is an error, right? Because SF is what we need to put, we are giving is S naught. So whatever the error is coming here, that will act as an error to our result, right? So this is something that we need to understand. Further, the numerical method is used to solve equation can introduce errors. Like in previous example, we have seen the technique, numerical technique that we adopt, that also can potentially introduce errors. Okay, so next come how to minimize is we do model calibration. Now, model calibration means you should have some particular data set whereby you have the input and you also have output. Now this output, what I mean by output is somebody should have a major discharge. Okay, somebody should have a major discharge at that reach. When certain input you are providing, you should have certain output. Okay, let's say for normal cases, if you just impinge a normal discharge of some normal Q, then if you have the output value, based on this you can calibrate your model. Calibrate your model means tweaking some parameters such that your solution is much more closer to the output, that is observed value. Usually it is not, it is a difficult for flood modeling, but for rainfall runoff modeling, this is one of the most important step in modeling. Okay, for flood modeling, however, because flood modeling itself means, we are generating for flood and we may not even have this output. Although I said if you have that, if you have is very difficult, especially in a developing country, that if you have does not really work because we don't have it. So there comes the main issue, and for flood modeling this becomes a major issue. Okay, because we cannot calibrate, we may not have the observed data. So that is one issue. However, model calibration, if you try to tweak some parameter based on your observation, based on your judgment, then of course you can produce a realistic result. Finally, there's also known as one more important step, validation. Now validation, usually for rainfall runoff modeling, we do this validation. You take a complete time series, let's say for 1 year, you use that 1 year time series as a calibration period. You use that period, use that data to tweak some parameters so that your result is very close to the actual output. And then you choose another year like 2018, 2017. You try to now once you have calibrated your model, you try to test your model on the validation period. So validation, that will give you an understanding how well your model is actually working. So this comes in rainfall runoff modeling. It's one of the most important thing. But for hydraulics modeling, validation becomes a challenge, because now of course we can do it in an approximate manner, we can do it, but actual manner, it maybe it would impose a lot of challenges to validate our results. So that's why I say it should be taken as a guiding principle rather than exact. It's not going to give us the exact answer. Now these are some cases, okay, where I feel the modeling would have really solved this. Not necessarily solved, but it should have provided us enough information to not to go into this it would not have this much of chaos if we have done a little bit of a study. These are in Bhutan, okay, and unfortunately these are very close to where I stay right now. So recently I went to this site. This bridge is completely buried under debris. So water is not flowing under the bridge, water is flowing above the bridge. So you can see here, this is not any flood, it's a debris flow. It's not a discharge. This bridge is not covered by flood water. In fact, it is covered by debris. So here comes a judgment of a modeler, the person who is doing the modeling. If you use discharge simply as discharge, so you set up your hydraulic model and you simply use water as, let's say, 10 meter cube per second to do the modeling, of course the result is completely different than what is observed in the real world. So as a researcher, we also need to identify the problem well. Just because you have a software, you can calculate discharge, simply don't dump that discharge into a model and run it. You need to identify the problem first. Identification of problem is more important than trying to do the simulation here. So that is what I feel. It's completely an ignorance from hydraulic side. Structural engineer must have done all the nitty-gritty calculations that he needs to do and constructed a bridge. But on the other side, the hydraulics of the region was completely ignored. That's why it's newly constructed bridge. It's not old bridge. It's a newly constructed, and people were aware of the situation there, yet they ignored completely the hydraulics, and then they land up in this situation. Last time I visited this area, now a little bit of this bridge is visible. They have started digging this, and now the top portion is a little bit visible. Another case is there's a bridge. Okay, from this image you can make it out that the depth of water is very less, because you can see the chain of excavator is completely visible. So depth is not more here, right? When this bridge was constructed, they have kept nearly 5 meters. This water was flowing 5 meters below this bridge when it was constructed. Just in one flood, there is a deposition of 5 meters. So this is another case whereby simply using a discharge or some values while modeling may not solve, I mean, you may not get a realistic results, because here the sedimentation is completely ignored, right? So you can see this bridge was nearly washed away just like this. So people, intervened, and they use excavators to dredge out the sediments. And later on, right now the depth, right now if I go, it is about 5 to 7 meters. So I don't know for how long it will be there, but still I feel that this is also an ignorance of hydraulics of the region. So these kind of, there are so many situations. If you just browse along, not just in Bhutan, recently a bridge has collapsed in Nepal. Maybe there's an ignorance from the construction side, or could be an ignorance from a hydraulic side, I don't know for sure. But of course, using a model setup can pretty much gives us an understanding how the system would behave under different stimulus. So these are some of the images nearby. So to summarize my talk, the disaster cannot be avoided completely, but we can do a lot to predict its occurrence through modeling and prepare disaster plan before that happens, right? Modeling can help us prepare hazard map. We can act as a baseline for policy making. So that is the main reason of doing flood modeling, at least for flood modeling. So when I'm on this disaster topic, let me also introduce you with the Center for Disaster Risk Reduction and Community Development Study at College of Science and Technology. So this is a very newly established center. So we are working to, our vision is to become the Center for Excellence in Research in Disaster Risk Reduction and Community Development Studies. It's a very new center, and I see a lot of opportunities to collaborate with universities like yours, the Central University of Jharkhand, and many other universities. So you can get me. We can contact. I mean, you can contact. You can go to this page, and you can, we can contact. We can, collaborate in any different disaster sectors. Okay, just as an information. Now I would like to briefly touch upon the hydraulic reference. Is also important, and I will not invest more time because it is already taught to you in classroom. So I'll simply brush through this concepts, and finally I will discuss the Polabram case. Okay. So for 1D steady flow analysis, I said the HES-RAS uses the energy equation. Energy equation, as we know, this is derived directly from Bernoulli's equation, right? So this is the Bernoulli's equation in open channel flow. So here they use the standard step method to solve for the water profile, the depth at the downstream. Okay, so this equation is solved iteratively when you use 1D steady flow. 1D steady flow means you will only put QP or one Q value, not the time series, but just the Q value. If you put in your HES-RAS as a boundary condition, that is what is known as the steady case. So if you do that, HES-RAS will use this equation, not the Saint Bernard equation, not the shallow water equation. It will use this equation to solve for the depth and the profile. Okay, so this is the setup. I believe we all know. Now one limitation as per the HES-RAS manual is, let's say this is the channel bottom. Okay, I'm just drawing a channel bottom here, just a plane. So one limitation that HES-RAS says is the depth that we are interested or we measure normally is this depth. Okay, this depth. And the HES-RAS uses this depth. This is the depth that we put, and HES-RAS actually, this depth d cos theta is used for calculation, whereby this is the theta, this is the theta slope. Okay, so if your slope is very high, if their slope is low, then d cos theta is much more equal to d for very small value of theta. For high slope, for a steep slope, then this is not equal. So there would be some error introduced if we use 1D for steep slope channels. So this is what HES-RAS manual says. Okay. Now how exactly it solves is, now only unknown parameter here becomes the, this HE needs to be approximated, and accordingly you need to find the depth. So HE, that is the frictional losses, is calculated using this equation, whereby this is the coefficient of contraction, then velocity head at upstream, velocity head at downstream, times, and okay, this plus the frictional losses. Now here L is a bit confusing because I said in a meandering river, the L, the reach length, the L is different. So this L and this L is different. So in this case, what they're using is they're using the discharge weighted reach length, which is calculated by this equation. Okay, so here they're using the discharge weighted reach length, not just the reach length. Okay, and next is, I said HES-RAS has the abilities to, to take in various Mannings at different floodplain. So right of floodplain, you can use different Mannings. In the channel, you can use different Manning. In the left, you can use different Manning. Yes. So now we need one Mannings roughness, which is also known as equivalent Mannings roughness. So equivalent Mannings roughness is calculated by this equation. So this is also the Horton's equation. Okay. You cannot make average of this. Arithmetic average doesn't work with the Mannings because it has a unique dimensions, right? So this Mannings, the roughness, the equivalent roughness is calculated using Horton's. There are others equations also available, okay, to find the equivalent roughness, but HES-RAS uses the Horton's. And as I said, now once you distribute this floodplain into right of bank and left of bank, definitely there is going to be a different velocity, right? There's going to be a different velocity. For standard step method, we have to use one velocity, that is the average velocity. So to calculate average velocity, what we need to do is they do the averaging of the velocity, and this coefficient, the correction factor, is calculated using this. Now how they come across this equation is that entire derivation is available in manual, which I recommend you to go through before you start with your HES-RAS journey. But this, in a simpler term, this is, it uses the convenience concept to calculate the alpha, or the correction factor. And here are some limitations. Okay, in the flow, in the 1D flow, the limitations, like I have discussed, for less than this is not advisable. They don't recommend using it less than this slope. Okay. And what are the limitations? The flow is gradually varied. All these locations can be flow can be rapidly varied. Momentum equation, other equations are used. Okay. Sometimes HES-RAS manuals also says that for bridges and culverts, they use some empirical equations is also used. Okay. And flow is one-dimensional. Like I explained, the component of velocity along the flow direction is only considered. The flow components, velocity components in right and left is ignored. So that is the limitation. Here comes the one-dimensional unsteady flow. Now here it solves the Saint-Venant equation. If you input discharge as a function of time, which we call it as hydrograph, then the HES-RAS solves the Saint-Venant equation. So you can see this is the Saint-Venant equation in conservative form. So if there is no lateral, so this is going to be 0. Lateral means if something is coming from the edges. Okay, so if there is nothing is coming from the edges, so this will become 0. And this is continuity equation, this is momentum equation. These two equations are solved using the box scheme. So this is what I have already discussed. I don't want to go it again. So this is what HES-RAS uses. Okay, so solve the shallow water equation. it uses an implicit equation. That's why a boundary condition is required. For implicit equation, downstream boundary condition is required, upstream boundary condition is required, and also the initial condition is required. From my experience, HES-RAS did not run if you don't put initial condition. Initial condition means what was the situation before you impinge the hydrograph. So it could not run with the empty channel. You should have some water previously running into the channel, then only it used to run. But now the latest version, I just heard that from some YouTube videos, I heard that now it can also use in empty channel. So even if you put the empty channel here, means without the initial condition. Okay, now finally comes our Polabarum case. Okay, so this is what I was exciting to share about. So okay, so Polabarum is the dam is constructed, I believe, in Andhra. If I'm wrong, please correct me. I'm not an Indian. Okay, so Polabarum Dam is, I believe, it is constructed in Andhra. The Godavari River is coming from Telangana, and one or two of its tributaries, like Sabri and Sileru, is coming from Odisha. So now people have constructed the dam here in the Polabarum Dam. So the backwater. So our main interest was how would this dam, cause a backwater effect on the upstream side. So that was our main interest. So this is our complete setup. And by the way, setting up a two-dimensional analysis in HES-RAS is very straightforward. Nothing. You just need a digital elevation model. You make up the grids the entire study area, you need to put it up into the grid, provide the boundary condition, and run. That's as simple as this. Okay, so two-dimensional, it's the hassle of making cross sections and so many things is completely avoided in two-dimensional. Okay, so the running is very simple. To run the model is very simple in two-dimensional, but the principle, the mathematics, the hydraulics behind this two-dimensional it's kind of challenging to understand. So what we did is, for Godavari, they have provided us with the PMF. Okay, I don't know whether this graph is visible to you or not. Let me again trace this with the black so that it becomes very clear. So this was the hydrograph at Godavari, and you can see the peak is nearly 100,000. I cannot even think of this much of water. So this is the peak for PMF, probable maximum flood, at Godavari. So we have impinged this from the Godavari. I believe this area, what is this area 5 is Dumgudum. So from Dumgudum, we have impinged this PMF as a boundary condition to the main Godavari river. Next was the Sabri. So Sabri has about nearly 5,000 cumecs of meter cube per second of water, so which was impinged from Sabri reach. And finally, the Sileru also contributing about 2,500 meter cube of water. So we have impinged these three. So in my case, I have three boundary conditions. One is from Godavari, that is the PMF is coming. One is from Sabri. Another discharge hydrograph was led to pass through this, and again from Sileru, another discharge hydrograph was available. And at the Polabarum, we had the major dam, and the downstream boundary condition is constructed way below the the dam side, so that now the downstream boundary condition, if you don't provide, then your entire area has nowhere to water to go. So your entire area will fill up like a bathtub. So that's why we need to provide this downstream boundary condition. This is the region where water will get out of the system. This upstream boundary condition is the condition where water will get into the system. And these are the grids, whereby two-dimensional grids. So the equation is the momentum and continuity equation is solved at a particular grid. And this entire area, although I have shown very small, the entire area is lot of this distance is more than 100 kilometers. It's more than 100 kilometers. 100 kilometers. Okay. Oops. And I have written it less than, but it's more than. It's it's more than 100 kilometers. So we have a kind of extensive area So to do this simulation, we took about, within a high-end computer. So there was a workstation in IIT Roorkee. It took nearly 17 hours. For some cases, we did number of simulation. For some cases, it took 17 hours to complete the simulation. So you cannot even think of running this model in my personal computer. It will run forever. So the most important of this is, as I said, the other things are very clear. Okay, there is nothing, the geometry, everything is taken from the digital elevation model. So as such, there is no much of hassle. Like in 1D cases, you don't have to provide the cross sections. Only thing you need to provide is the dam information and the boundary conditions. This is correct, then rest will be simply the having the topographic data, the model will simply run. Okay, so like I said, the boundary conditions, these are more important. Okay, so the most important thing that I would like to discuss here is, I have already discussed about the hydrograph boundary condition, and the downstream boundary condition is given as the normal depth. In fact, it asks you to provide SF, but we give S0 because SF is not available. So that is what I've explained. The most important here is the downstream condition of the gate or the dam. Okay, so here we have provided the elevation controlled gates. Okay, so the boundary condition for the gate in the dam was elevation controlled gates. What I mean by that is, let me draw a simple diagram here. So let's say this is our dam. This is our dam. So our condition is, as the water reaches a level of 45.72. So this is the maximum water level in the reservoir. As the water reaches this elevation, then gate should start to open. So they will have some gate, right? So gate will start to open when the reservoir is full. Since we were interested to see the backwater effect, and our condition was the dam is full. When the dam is full, then the PMF is coming. So that was the condition we were trying to see. That is the most extreme cases. Okay, that is the most extreme case. There's nothing beyond this. Your dam is full or your reservoir is full. On top of that, the peak PMF is coming. So that was our case. So our condition was, as it reaches the 45.72 meter elevation, then gate should start to open, and gate the rate at which the gate was, this was kind of approximated. What we said is, in 1 minute the entire gate is opening. So these values were not exactly available, so we had to approximate this. And when the water level is at 25.72, then gate would completely shut. When the water level is 25, the gate will shut. When the water level is at 45, the gate will open. So that was our condition. Okay, so with this is the final. Of course, there is plenty of animations and the velocity profile and so many other stuff, but as an engineer, I think this graph becomes more important and useful for us than those fancy stuffs, right? So I would like to throw a question here. If somebody could explain this graph. Let me first explain the situation here. There is a dam. There is the Polavaram Dam, is a top view. Okay, there's a water coming in. Okay, and there's a water going out. So this light blue, this let me trace this with some different colors so that it becomes very clear. I don't know whether it is how much visible it is there. So let me put a different color with the red, I believe. Okay, so these, I'm just tracing this. Okay, so that it is much more visible to you guys. Okay, so this is the headwater. Headwater means at the upstream of the dam, and the blue is at the downstream of the dam. So these two plot is the stage hydrograph at upstream and downstream. So now my question is, why there is a bulge here? So that is, I mean, it has some interesting logic. So this is the simple question that I would like to throw to the audience. If somebody could answer this. So I will just run over the other slides, but in this meantime, you can think about the answer. So that is my discussion. Okay, that will be a discussion. If you don't have any questions, so we can discuss on this. So why there is a bulge on this? So So that is my question. Okay, you can think over it. And like I said, you can get pretty fancy stuff. This is the water surface elevation at the maximum depth. So, and another interesting case that we have observed is, there is a small gorge here. So this gorge is acting like the constriction, and there could be a choking effect here. However, we could not completely justify choking is, there could be a choking. We didn't have the time and luxury to do the study here, but we anticipated that more than this dam, there is a choking effect going on here, because dam is able to pass the discharge, but this choke, because of this choking, the water level because you can see from the color difference, from this choking only that the raid started. So that was our interpretation. Anyways, people will have different interpretations here. So this is one, the flood hazard. In a sense, you can say the flood hazard map also you can derive from this one, but this is the water surface elevation at the peak maximum depth. Okay, and here is the backwater curve. So this is along the Sabri center line. So now you see that the issues here, this all spikes is all because of the digital elevation model. We have used 30 SRTM data, so not very good for doing such modeling, but still then we didn't have anything to use as an input. So we use 30-meter SRTM as the data, and this is the water surface elevation when you construct a dam, and this is how it looks 25 or 20 kilometers away from the confluence. Okay, and for beginners, you can get most out of HES-RAS if you subscribe. I mean, I'm not paid for this. I'm not paid for advertising this, but it has a lots of useful information. This RAS solution, a channel in channel in YouTube, it has this channel has lots of useful videos, and most of the fundamentals I developed from watching this video. More importantly, there is a discussion with Gary Brunner. So you can see this video, episode 13 and episode 12 is a discussion with Gary Brunner. And if you ask me who is Gary Brunner is the father of HES-RAS. In a sense, he is the person who is behind HES-RAS software. Right now, I think he recently retired, but this is the guy. So it's about 1 hour 46-minute long for one video, and another video is 1 hour 15 minutes long. They discuss nitty-gritty of HES-RAS. This guy discussed in detail. So if you're really interested to learn more about HES-RAS, please go through these videos. Okay, so with this I would like to end my talk, and I believe I am 12 minutes. Okay, so it is Bhutan time, so I think we have some time, right? So let me go back to same slide and start with the discussion. If you have any other questions, I'm happy to share. If I know, if I don't know, then I'm sorry. So these are the this is my question to the audience.
Yes, if anybody has the answer, he or she can unmute yourself and respond to the question.
Sir, backwater curve.
Okay, so first answer I got is this is the backwater curve. Okay, fine. Interesting. Any other?
I can write in the chat box also, if you don't want to speak out. Mr. Kirtan, we
Yes,
have
sir?
few questions in the chat box.
Oh, okay. So let me check this.
Yeah.
I'm not quite used to it. This chat box is okay. Hi, can DEM is enough for 2D urban modeling? Now, urban.
One
So, first
question is
question.
there from Sivasis Panda.
Okay.
Sivasis,
Now, let me go back to my screen here. So, the first question is maybe he is asking from this image. So, is it enough for DEM, only DEM as the topography data for urban flooding? So what happens, we need to understand that what is DEM and what is DTM. Okay, there's two concepts. One is DEM, digital elevation model, digital terrain model. Okay, so there are two concepts here. So let me explain this and maybe that will answer your question. Okay, digital elevation model means it will not take into consideration all the features that are man-made. For instance, the buildings and so many other stuff, these are not taken into consideration when they generate DEM. It is simply the topography. Okay, it is simply the topography. What should I write? Maybe somewhere here. Okay, there's not enough space to write here, but anyways, I was just looking for a place to write. So in digital elevation model, let me say I'm writing this here. Okay, I'm sorry, there is no enough space. So in digital elevation model, if there is an if there is an house here, if there is some kind of structure here, these structures are ignored. Okay, these structures are ignored. There is a forest here, there is a forest here, these forest is also ignored, and only the ground surface is taken into consideration. So when you say urban, I believe these structures are important. Yes. So for you, it is not the DEM, it is the DTM, digital terrain model. Digital terrain model has this kind of features in it. So if you have digital terrain model or a LiDAR data, then of course you can go for a if you have that data, yes, of course you can use it, but only with the digital elevation model. As I explained, these structures are not there. These structures are removed. It is only the plain ground. So that main impact, that you want to do the urban modeling, but without an urban situation, you will end up doing modeling of urban but without the urban setup. So uh, the answer is, direct answer would be no, but if you have the data set, of course you can go ahead.
Suman Dev Burban is asking that, sir, you please repeat the question which you asked
Hey,
earlier.
okay, that is an interesting one. It was, I mean, it was really
Yeah.
fun to having this kind of situation and analyze in front of professors. It was fun. So my question is, this is the stage hydrograph. Okay, stage hydrograph. There's a dam here. There's a dam, Polavaram Dam here. The red one is the stage at upstream, and the blue one is the stage at downstream. Okay, that is the case. And this graph shows the stage hydrograph. Stage means the elevation. The stage means the elevation from the ground with respect to time. Okay, so this graph is the stage with respect to time. Now, my question is, why there is a bulge? What is happening, just in case, if I need to elaborate more, what is happening is at this time, the gate is opening, okay? I said at 45, the gate is opening, right? At 45.72 meters, I'm opening complete gate. So when I'm opening the gate, let's only take for the upstream case. When I'm opening the gate, suddenly the stage is dropping. Of course, when you open the gate, discharge will increase, but the stage will drop because you are letting off the water. But again, you see there is a rise. Why there is rise? So that is my question.
I have got two answers from Amit Raj. He is saying that this is a positive surge, and Chitranjan Dalai is saying that this is hydraulic jump.
Okay, interesting, very interesting. I can see that my audience were not sleeping at least. Thank you, guys. So, just to cut things short, okay, let me give you an answer. What is happening is now we need to really think of so many other parameters here. So it is not because of surges, it is not because of hydraulic jump, okay, it is about something else. Now let me explain this, what is happening. Okay, so I will go to my first setup. What is happening is, I said from this Godavari, I'm giving a hydrograph here, right? I'm giving a hydrograph. From Sabri also, I'm giving a hydrograph. From Sileri also, I'm giving a hydrograph. So what is happening is, at the same time, I'm releasing these discharges. So this discharge is running. Oops.
Sir, may I try to explain, sir?
Sure,
Answer.
sure, please, sure.
Sir, as per your location of this dam, you mentioned there also a gauge. So when this sudden discharge, the stage hydrograph will decline. But as per your, sir, dam location, the gauge is very narrow. So the in that time, the water will try to uh, stored in this dam and this portion. Yes, sir. You told that there also a gorge or this crisscross high profile. So this channel is very narrow. So with respect to time, this high discharge water coming from Godavari and Sobori will increase this stage height.
Okay, so thank you. So the main thing is, we are actually talking about the, whatever you have said is correct. Okay, whatever you have said is absolutely correct. No, nothing is wrong in what you're saying. But my case is, I'm talking about at this location, at the dam location. Okay, at this dam location, why there's a bulge. So that is my question. Whatever you said is absolutely right, but my case, you have taken this case as the gorge area, but my question is at the dam site. So at this dam site. So okay, so let me give you the answers. Okay, so as I was explaining, there are three hydrographs. Okay, one is the hydrograph that is coming from Godavari, another one is the hydrograph that is coming from Sileriu, and another hydrograph that is coming from the Sabari Ridge. Okay, so with the time, what is happening is, these hydrographs are getting routed here. Okay, these hydrographs are getting routed here, and at the beginning of time, the dam is completely, it's not completely empty, but some water is there. But our condition was, we have to release the water only when the water surface elevation at this point reaches 45.72 meter. Okay, so that was the condition. Back of the head, we need to understand that was the condition. So moreover, this discharge is not a small discharge, it is huge. We need to understand, a lot of water is flowing. Okay, so what is happening is, before the peak arrives here, okay, before this peak arrives here, dam is getting full. Okay, so dam is getting full before the peak is arriving. So let me erase everything. Before the peak has arrived, the dam is already full. Okay, the dam is already full at this point before the peak has arrived. Okay, so dam is full. At this time, at the 11th hour, okay, at the 11th, maybe sometime after 11th hour, let me take it as 11th hour. At the 11th hour, the dam is full. So now once the dam has reached its critical level, we have to release the gate. I'm releasing the gate. So as I open the gate, lot of water is running out. So that's why when the water is running out, nearly 10-meter depression is observed. Nearly 10-meter depression, in the sense, upstream of the dam, that much water level has decreased because I am opening the gate. But the peak has still not arrived. That is the main answer. Peak has still not arrived at the dam. So this bulging is because of the peak that is arriving in the dam. And one more interesting thing that we need to observe is, if this peak has to be lower than the critical depth, that is 45.72 meter, this peak should not have exceeded this. or else that would implies that the dam was not designed properly, because it couldn't, the maximum PMF would have overtopped the dam. And this was a good thing. There's a pretty good margin, about how much, about let's say 2 3 meter of margin, even when PMF is coming, when the dam is full, which means it is also implies that the dam was pretty good, it was designed perfectly so that it can completely pass the PMF flood. It is a lot of water. Okay, the answer to my question in a long talk cut short, the answer to this bulging was the peak is arriving after the dam is full. After I have opened, then only the peak is arriving. And when the dam is open, completely open, okay, when all the gates are open, it is able to safely pass through the peak discharge of PMF. So that is the answer. Anything else?
Mr. Kirtan,
Yes, sir.
we have a question from Sivasis Panda.
Okay.
How to avoid flood when there are river disputes in some parts or states in India? This is a general question, but maybe of interest.
So I could not completely understand the question.
Yeah. How to avoid flood when there is a dispute that between the states?
Okay, so how to avoid the flood? I mean,
yeah, this is a policy matter.
It's a kind of a policy, but now I don't have a perfect answer, because it may not even have a perfect answer to it. So when I talk about how to handle the flood, if you ask that question, let me change the question on my part, okay, because I'm unable to answer your direct question. So let me answer the way how to avoid the flooding. So yes, here comes the HES-RAS modeling. If we have such a model in place, done prior to any development activities, then having the data in front of us, we can, the policymakers can, the engineers, because they have already data, we can construct, or we can go on with the development according to the data we have. But if you ask me how to avoid the flood, or now flooding is primarily governed by rainfall, right? To avoid the flood, you have to avoid the rainfall, which may not be possible in our case. But as soon as the flood is coming, how to deal with that flood, that is much more an interesting, it is what an engineering problem is. So that for that, perhaps a modeling would help. So that would be my answer. Maybe I did not answer completely, but
maybe like that. This may be related with the release of water in the upstream side where one state is lying, and it may be that on the downstream side there is another state. So states should work on that, when to release the water or that when to hold the water. So Sivasis Panda, is it fine with you? So the releasing of water may be an issue between the states. Now the upper part is full, so they would like to release the water. So maybe the downstream side states may face some sort of problem. Am I correct?
Yes, sir.
Yeah.
Yes, sir.
Yeah, fine. So, but if you see the national water policy, we have interstate dispute provision, and such issues are resolved by this. But yes, that's an issue. That's an issue. Even states don't come together to discuss such issues.
Okay, sir. Thank you.
Yeah. Amit Raj is asking that Mr. Kirtan.
Yes.
How can we use HES-RAS for modeling seasonal rivers, which have peak flow during rainy season, but no flow or lean flow during other months?
Okay, that's an interesting one. So Again, I will go back to my slide. In the first slide, where I have shown you the river networks, I have been scrubbing so much. I did not realize I have been scrubbing so much.
It was a very nice
Okay,
lecture. Yeah.
so I think your question is much more related to how to model a river that has so many, the tributaries, and moreover, it is dry, completely dry during winter, and completely, there's a huge discharge during summer. So, friend, it is like
Advanced.
this. We do not do modeling for when we talk about the flood modeling. We do not take into consideration the lean season because we are not interested in lean season. We only take into consideration the peak discharge that is expected, like the PMF or the standard project, or there are some other design project floods. So these floods are taken as a case study, and we only simulate for that cases. So now if there are so many rivers here, so every river will have some hydrograph, right? It will have some the critical hydrograph. I'm talking about the critical hydrograph. So this is where we want to estimate the discharge. So for one dimensional, you have to provide the cross section details of all the rivers. Okay, all the cross section details of the rivers. For two-dimensional, like I have shown in the Polabaram case, Polabaram is also a big, huge river, 100,000 cumacs of water. I cannot even imagine. Complete water in 1 year from Bhutan may not be adding up to 100,000 cumacs. That much I'm sure about it. So, okay, this is a huge river. So, if just to answer your question, we don't do flood modeling for entire year. Okay, we just pick up particular cases. Just last time there was a Kedarnath flood, so that discharge is what we are interested, because that is the discharge that will cause the flood downstream, right? So it's only event based modeling, not the continuous modeling, that distinguishes it from rainfall runoff modeling. Rainfall runoff modeling, you do it for continuous stretch of 1 year, 2 year, 10 years. But hydraulic modeling, we don't do that. We only do a case event, just one PMF or one hydrograph. But if you are doing for one dimensional, you need to provide all this cross section TDS. So we do it for two dimensional. So for two dimensional, just provide the boundary condition, provide your discharge hydrograph, click the run button. That's it. It's very straightforward.
Hello, sir.
Yes, yes.
Sir, in West Bengal, Moirakhi River Basin, there
Mhm.
are also some stretch 4 kilometer. There are
Mhm.
several last 2 years sand mining. So
Okay.
if I want to judge this effect of sand mining on channel, so
Mhm.
sir, HES-RAS model how to help?
Suman, I believe it is Suman, right, who is speaking right now?
Yes, sir. Yes, sir.
Okay.
Suman, sir.
Yes, Suman. Suman, HES-RAS has one more capabilities which I did not discuss here. It can take into consideration the change in bathymetry. Bathymetry means now maybe I did not. Did I put? No, I did not put here. So this is a recent in recent HES-RAS model. What they have is they have this. If this is the original bed, okay, let's consider this as the original bed. And as you say, because of sand mining, of course, the bed is going to go like this, right? Yes. So this
Yes.
analysis HES-RAS has in 6.0 and beyond this, HES-RAS has the ability to do this kind of analysis. You just check it out the manual. Yes, HES-RAS has this ability in the latest version. Old version it does not have. Latest version it has. Sand mining basically means you are disturbing the bathymetry. That's it. So it has this. You can do this study in HES-RAS.
Oh, okay, sir. And sir, for that case, just upstream, downstream boundary are required, sir.
Yes, for HES-RAS, upstream is absolutely required because you need to put in some discharge. Downstream, you can simply put it as the channel slope. You will have some channel slope. So downstream is not a big concern. Upstream, you need to put the discharge hydrograph. Okay. So this discharge hydrograph, you need to have it. If you don't have the discharge hydrograph, then you can approximate it. You can do some kind of, rainfall runoff analysis of the catchment, and a little bit upstream of your study area, you can do the rainfall runoff. So from rainfall runoff, you can get this discharge. At all, that is also not available. Then you can try doing some 1D steady analysis by hypothetically assuming, by you can go to the site and observe what is the velocity of the river, and then you can approximate discharge. Using that discharge, you can do 1D steady analysis. That is also possible.
Oh, okay. Thank you, sir.
Okay, if anybody want to ask any one or two question, they can ask directly. Abu Libda, you can ask him. Okay, Mr. Kirtan. Yes, we will close the session here.
Okay, sir. Thank you very much for having me here. I hope students something to take away from my slides. I will send you the slides. Please share with the students.
Somebody wants to speak. Mohan, please unmute yourself and ask your question. Somebody raised. Okay. Mohan Babu and that many more, they have appreciated your lecture. This was a wonderful session. Divya, you want to ask?
Welcome, Mr. Suman.
Okay, sir.
Okay, sir. Thank you very much for having me here.
Yes, that we are very thankful for you to accept our invitation, and you have presented a very deliberate lecture, especially the equations and the solutions. We have already said all that hydrological model, hydraulic model, and even the groundwater model. All those models are based on nonlinear equations, and solutions are there using numerical techniques. So very good understanding of the equations are needed. So those who are interested in the modeling work, they must understand all these equations and the solution. So Mr. Kirtan, this was a wonderful session with you. Even I have also learned so many things, and we hope we will meet again.
Sure, sir. We should definitely put an effort to meet.
Yes, so this was a very nice experience with you. And I'm saying, yes, Mallika Jain is writing very knowledgeable presentation. Anjali is writing, yes. Suman Dev has appreciated. Amit Raj is saying, thank you. Gajendra Kumar is writing that this was an informative session. So everybody is happy, sir?
Thank you, sir. I'm very happy to know that everybody got something at least.
Yeah.
So I will share with the notes with you. Please share with your students. I put all my effort to educate my students. So it has to be shared with the students.
Yes, please. Sivasis Panda is writing very informative and constructive, sir. Yes. Thank you, everyone.
Thank you.
Amuta is writing nice presentation. Yeah. So everybody is happy, Mr. Kirtan.